Good morning and welcome back. Uh, in the previous class, we were discussing about the different variant of load configurations, and we saw if we have some P-type MOSFET, N-type MOSFET, and then we also discussed about if we have some depletion kind of MOSFETs as well. So how this will behave and how it can work. Okay, so these things we have already discussed. Okay. I'm expecting you all know how it is working. Okay, so perfect. So let us start one simple inverter
Hello, sir.
configuration, and let us try to analyze few of the
Hello, sir.
parameters. Yeah, please.
Sir, the last case yesterday I had asked to discuss again.
Okay, fine. Okay, let us discuss. Okay, so fine. So let me change the color. Fine. So how this circuit will behave? Initially, let us assume if V in is equal to 0. Okay, so let me draw this diagram in the fresh page so that you will be able to understand perfectly, right? So yeah, we have one. Yeah, I'm just drawing here. It's not, don't consider it like resistive load. I'm just making it here because we have the plain sheet here. Okay, so this is the structure in the previous slide. Okay, so let us try to see. Yeah, do not consider this is not a resistive load. Okay, so don't consider it like this. Okay, so let us consider two different cases. Suppose if V in is equal to 0. If V in is equal to 0, in this case, let us assume I have this one is M1 and this is M2. So what will happen? This M2 will be in off state. Okay, now let us try to check what is the status of this M1. So because this is the gate, this is the drain terminal, and this is the source terminal. Okay, and now here if we see, because I have connected this is to the like initially I'm also considering this capacitor is initially discharged. Okay, so whatever capacitor we have connected, that is discharged. So the VGS for this one, like the M1 is VGS, this is equal to 0. And we know that what is the current equation for this depletion kind of MOSFET? This is ID is equal to IDSS 1 minus VGS divided by VP whole square, where this VP is the negative value for the N MOSFET. So this VP is the negative value. Okay, now if you see here, if Vin is equal to 0, this M2 is in off state, and because this VGS is equal to 0, this particular component will become 0. Okay, sorry. So if this VGS is equal to 0, this component will become 0. So what it means, ID is equal to IDSS. So some saturation current will flow. What it means, the transistor M1 is in the saturation region. Okay, so M1 is in on state and it is in the saturation region. Okay, so this is how it will work. Okay, now let us talk about further what will happen with the other conditions. So once this is saturation, then what will happen? This capacitor will start charging through this one. Okay, so this transistor will lead to charge this one. So I'm expecting if it is the N type of MOSFET, this will completely transfer the logic. But what will happen? This VDD will be charged, this capacitor will be charged through this M1. And once this, we know that the characteristics of the N MOSFET, depletion kind of N MOSFET is something like this: VP minus VP and something. This is the VGS. Okay, so what will happen? Once it will start charging. Okay, And once the source voltage reach equal to the VP, okay, so at that time I will get VGS is equal to VP. Okay, so that will, yeah, I'm considering the modulation only. Okay, so once this capacitor start charging, because this is in the saturation region, so this VDD will be transferred to this way out, but this capacitor will start charging, and once it reached up to this voltage level like VP, what will happen further? This it means the VGS is equal to VP, right? And again, if let us assume this capacitor is charging with the more value, so what will happen? This VGS will become like this, magnitude of this VGS will be even greater than the magnitude of this VP. Okay. So what we can see here? We can see here that the device will be in the off state. Okay. This device will come into, because the VGS is going into in this direction. Okay. So device will be in the off state. So the maximum value that it can charge up to the VP. Okay. Now this is the case when we are talking about the input is equal to 1. Now let us talk about the input is equal to 0. Okay. Sorry, input equal to 0 we consider. Now let us talk about the input is equal to 1. If input is equal to 1, in that case, what will happen? Transistor M2 is in the on state. Okay. Transistor M2 is in on state, and then let us see what is happening with the VGS of M1. Okay, so the VGS of M1 will be something like here G is equal to VDD, and initially let us assume the capacitor is discharged. Okay, initially I'm considering for both the cases capacitor is discharged. Okay, so later on we will check it out. Okay, so if the VG, yeah, so this is nothing but this becomes the VDD, this voltage becomes the VDD. So the VGS is nothing but initially it will be like, see, this capacitor can charge up to VDD at max. The maximum limit could be like this CL or the voltage across. Let me write it perfectly. The voltage across load capacitance, this can vary in between 0 volt to VDD. So this is the minimum and maximum range. If VCL is equal to 0 volt, in that case I'm considering this particular case, right? So in that particular case, what will happen? This VCL is nothing but this is equal to VS for the M1. Okay, and because I have provided the VDD, so the VGS for M1 that will become VDD. Okay, that is equal to the VDD, and if it is equal to VDD, what it means, the device is in the on state. Okay.
Yes, sir.
Right. And similarly, let us consider and what is the and if VCL is equal to VDD, okay, which is equal to the VS of M1. In that case, what will happen? This is the VS.
On state.
So the VGS M1 will become like here. We have the it will be the 0 volt. So again, this transistor will be in the on state. So both the transistors, like if I'm considering Vin is equal to 1, in that case, both the transistors will be on state, and both the transistor will act means the whole circuit will act as a voltage divider circuit. Okay, and if it is acting as a voltage divider circuit, what it means, the output voltage will be that depends on the value of transistor sizing, like M1 and M2. So if M2 is more stronger, so that can pull down to more value, and if M1 is stronger, that can pull down to the upper value. So this is how this will work. Is the point is clear?
Can you draw the characteristic final one?
Characteristics. Okay, so the characteristics will be like this one. Let us see. So if, let me assume I'm increasing the input something like this. Okay, so this is the input, this is the output. Okay, what happens if Vin is equal to 0? I'm assuming that the output that can charge up to the VP. Okay, here it will charge up to the VP. And if Vin is equal to 1, in that case, it will try to, so because both the transistors are off, in on state, in other case, like if Vin is equal to 1, so initially this will be something like this. And because both the transistors are on, the maximum voltage that this capacitor can charge up to the VP only, not greater than that one. Okay, so if it is not greater than that one, so this will behave something like this. Okay, so this is the behavior.
Sir, why it can't go above VP in
Our,
the
because
second case?
huh?
In second means, sir, when both transistor are on state, what is happening?
In the second case.
Yes, sir.
Okay, so see here. So if both the transistors are in on state, so VGS here is like, if we see this case, VGS is equal to VP. So we can have two possible combinations, right? So either it could be like it can reach up to the VGS becomes the VDD, or the VGS becomes 0. Okay, and in both the case, the transistor is in the on state. But what happens? Yes. Yeah, I made one mistake here. I think the behavior will be something like, if it is 1, in that case, that will start charging, and the behavior will be somewhere here that can reach up to this one. I think it will behave something like this. Okay, that will act as a buffer kind of circuit. Yes, this is really very important circuit. Actually, I was not thinking about in this direction. Yes, perfect. Because in this case, if you see, like if Vin is equal to 1, in that case, this capacitor can charge with the maximum value because there is no possibility of cutoff. Okay, and if there is no possibility of cutoff, then the behavior will be something like this. So this can reach up to the VDD, and the circuit will behave like an inverter, like a buffer.
Sir, if I label the above resistance as R1 and below as R2, then it will be R2 upon R1 plus R2 times VDD, right?
Yeah, yes.
It will be some fraction of VDD by voltage divided.
Yeah, so it cannot reach up to the maximum. So it means that you have removed the resistance, like R1 resistance of M1 is very low. In that case, you can go up to the VDD. But yes, so this will be something like, the behavior will be something like this. Okay, and this is because of the W1, W of M1 is increasing. Okay, so if W of M1 will increase, then you can reach up to the VDD. So this is the behavior. You got the thing?
Yes, sir.
Okay, so I think instead of removing this one, let me add one more page so that will be saved with you. Let me add one more slide here. Yeah, I plan to act like this. Okay, I believe on the perfection, so I'm doing like this. Okay, perfect. So let us. Okay, so this was all about the previous circuit. I hope the points are clear. Okay, now let us talk about the resistive load, NMOS inverter, and its behavior, its characteristics in detail. So see, if you can go back to these slides here, we discussed the different kind of configurations which are acting as a inverter, or they are not acting as an inverter. And an important thing here, yeah, I need to mention one more thing, like this particular thing will not act as an inverter, but instead this particular will act as a buffer. This is wrong diagram. Okay. So this is how this circuit will work. Okay, so till now we discussed the different kind of variants. Like, so let us start with one of the basic circuit, which is the resistive load NMOS inverter. So this is the basic structure which we have already studied somehow. Okay, and let us try to understand how this circuit will behave, and what are the different combinations on which this will work. Okay, so let us consider one by one. Let us assume if V in is equal to 0. Okay, so if V in is equal to 0, what will happen? This transistor, let us assume this is the M1. So the M1 will be in the off state. Okay, so if M1 will be in the off state, in that case, the equivalent circuit will look like this one. Okay, so this is the equivalent circuit which we'll observe, and here we have the RL. So this output means whatever the output we will get, that depends on like what is the value of this resistance. So definitely we will get some output, and in that case I'm assuming that because this transistor M1 is in the cutoff region, and if it is in the cutoff region, I'm assuming that the current flowing through the device will be equal to 0. Okay, so because this one of the transistors is in off state, so the equivalent circuit will look like this, and the current flowing through this device will be 0. But what will happen if I'm providing the input, if V in is equal to 1? If V in is equal to 1, in that case transistor M1 will be in the on state. And if M1 is in the on state, then what will happen? The equivalent circuit for this configuration will look like this. Okay, so this is the VDD, this is the grounded. Okay, and here we are taking the output. This is the load resistance. This is the R on of M1. Okay, so what will be the ID? What will be the current which is flowing through here? Can anyone tell me what will be the current?
Sir, VDD divided by RL plus RM1.
Yes, perfect. So here we will see like ID will be approximately is equal to VDD divided by RL plus R on of M1. So here the important thing is to note here is like, initially I'm considering I need to design a circuit in a such a way that there should be no static power dissipation. What is the static power dissipation? Static power dissipation means if we have a fixed input state, in that case, the total power dissipation through the circuit is known as the static power dissipation. So in the first case, if we see, there is no current flowing through the circuit, but in the second case, the current flowing through the circuit, that completely depends on what is the value of this resistance and what is the value of what is the sizing of this transistor M1. Okay, so if the resistance is more, this RL is more, and the R on is more, in that case the ID will be reduced, and if ID is reduced, you can save the power, can be saved. But on the other hand, that will create some problem. What kind of problem that will create? Let me tell you. Okay, yeah, so if I want to check the logical function whether it is working as a logic or not, right? So if we see here, if input is equal to 0, then I will get the output 1. That is perfectly. So let me write here also the red color.
In first case, output is VDD, right?
Yeah. So it will be the VDD. Okay. So in the first case, output will be V out. And if you see here, this output, I'm assuming that this output should be low because this is acting as an inverter, but this output voltage becomes the function of this RL and the W by L of the transistor. Yeah, so let me write it perfectly. W and L. Okay, so this output, yeah, ideally I'm assuming that output should be 0, but it is not 0, and that completely depends on what is the value of RL, what is the W and L of the transistor M1. Okay, and based on that we can decide what is the output voltage if input is equal to 1. So what I'm assuming, if I'm assuming that if RL is very high, in that case, in RL is very high and W and L is very high. In that case, we can say that the W and L is very small. In that case, we can say that the ground will be transferred to the V output. So that depends on these things. So we will discuss all other things as well. So don't worry. I'm going to consider a few more things into the detail one. Okay. Let me consider one more thing. Here we have considered like the current which is flowing through the circuit will be 0 if input is equal to 0, and that current will be non-zero if the input is equal to 1. What it means? It means that the static power dissipation for this circuit is non-zero. So this is really very important. Static power dissipation is non-zero. Okay. One more thing. Let us talk about what is the effect on the delay. Okay. So how this delay is going to be affected. So if I'm talking about TPLH, okay. So TPLH, can anyone tell me TPLH will depend on which resistance? When TPLH will come into the picture?
Sir, when I am going from low to high.
Low to high. So that RL will play a major role on TPLH, right? Okay, because I'm charging the
RL.
yeah, so I'm charging the load capacitance. So whatever the load capacitance over here, I'm charging that load capacitance through this one. So if I'm charging, then this will there will be some constant K. What that constant is, we will discuss this later on. I'm not writing the constant because that K is having some different meaning. So let me write some factor X, for example. So that will be some factor X, then it will be multiplied with CL, and that will be multiplied with the RL. X times of CL into RL, that will be the TPLH. Now let us talk about what is the TPHL. So this TPHL is nothing but that is can anyone tell me what will be a TPHL? Let us talk about some factor X, then CL, and that will depend on the R on of transistor M1. So this is how the TPLH and TPHL will look like. Now the important point of consideration here is, if I have to make equal rise time and the fall time, or equal delay for low to high and high to low, in that case I need to maintain the equal resistance in both the combinations. Okay, but there is some problem. What is that problem? Let us try to explain it. If both the resistance are equal, so I'm talking about TPLH and TPHL should be same, so that you can make a symmetrical design. Okay, so the delay should be symmetrical in both the cases, in both the switchings. Okay, but if I'm considering like R on of M1 is equal to RL, in that case what will happen? This will act as a complete voltage divider circuit here, like this one, this case. And if it is like that, the minimum voltage that we can get, the characteristics will look like this one, and the minimum value that will be nothing but this will be the VDD by 2 only. Okay, you cannot go less than the VDD by 2. The minimum value of low logic that will be is equal to VDD by 2. Okay, so the problem is, the important thing is, yeah, so we'll discuss it later on, no problem. The thing is, so how we can overcome this problem? To overcome this problem, I need to reduce this R on. Okay, so if somehow I am able to reduce this R on, so the voltage across this R on will be lower, so this will be shifted in this direction. Okay, I will discuss it later on. Okay, no problem at all. So here the point of consideration is in the ideal case, the delay should be equal in both the states. But if I'm making equal delay, that is going to create some problem. And what that problem is, I just mentioned a few things, but later on I will discuss in detail. Okay, so this is this I'm going to discuss it again. Okay, no problem. One more thing. So let us try to see. Suppose I have a characteristics of this resistive load inverter. So suppose this is the resistive load inverter, and we got the characteristics will look like something like this one. Okay, so let me draw the diagram. Okay, V in and V out, and I'm assuming that the output characteristics will be, yeah, let me make the input which is changing something like this. These kind of characteristics are known as the DC characteristics. Okay, so you should know the things. So how the behavior will be, initially I'm assuming that for the lower input the output should be high, and for higher it should be something like this. Okay, so ideally I'm assuming that the VOL should be as small as possible. Okay, but the important thing is VOL completely depends on the sizing of the transistor, whatever we have, just we explained in the previous slide. Okay, so like let me draw the equivalent resistance of this one. So equivalent resistance will look like this one, and if both the resistance are equal, in that case you can reach up to the VDD by 2 only. Okay, and if you are increasing the size of transistor M1, whatever we have here, if we are increasing the transistor of M1, in that case this resistance will be lower down, and if this is lowered down, the output across this resistance or this transistor will also be lowered down, and you can shift the waveform in this direction. So the waveform will be shifted in the downward direction, or the VOL will be reduced if W of M1 is increasing. So if I keep on increasing the width of transistor M1, in that case you can pull down, or what it means, it is going to reduce the R on resistance of M1. Okay, so the R on M1 is going to reduce, and if it is reducing, the VOL will reach towards to the lower value. Okay, so you need to forcefully pull down the logic levels if the input is high. Okay, so this is the condition which you need. Okay, further we can also find some relation. We can calculate some of the values for the VOH, VOL. So I'm directly coming to the values only. But the derivation you can refer any of the book, because derivation is not that much important, but you should know the concept how it is working. Okay, so but I'm expecting that you should know how to calculate this VOH, VOL. Yeah, so if you will calculate the VOL, this is coming something like this. So this is very complex equation. So but yes, we need to check it out. What are the different factors which are deciding the VOL and the VOH. Okay. In the ideal case, what will happen if the strength of this transistor M1 is low, or it's something like moderate? In that case, you will get the VOH that will be closer to the VDD. Okay, but what happens uh, if you are changing the sizing of RL, that RL start dominating? Okay, so if RL start dominating, in that case the VOH also change, and that changes with some factor, all that start reducing, and that is equal to VDD, and that becomes 1 upon 2 times of Kn into RL. So this is the factor by which the VOH start decreasing if the sizing is going to be increases. Like see, if RL is very high, so this second part will be very less, and then the VOH will be close to the V out VDD. But if you have increased the strength of this M1, okay, to make the VOL lower, in that case the resistance of M1 will start dominating as compared to the RL. So this particular factor will come into the picture. So this factor will come into the picture if we are decreasing the size of if you are decreasing the resistance of M1, okay, or increasing the size of M1 to make lower VOL. Okay, so that factor will start that factor will come, and that will start dominating the RL. So VOH will be something like this. Okay, so this is a really very important parameter that you need to consider when this VOH will be VDD, and when this VOH will be the VDD minus 1 upon 2 Kn into RL. So the simple answer is, if the strength of RL is dominating and the size of M1 is less, in that case you will get the VOH is equal to VDD. Okay, but if we are increasing the strength of M1, in that case if the strength of M1 is increasing, in that case VOH will be VDD minus 1 upon 2 Kn into RL. So this is how VOH will look like, and this is the function, the factor by which it is depending. Okay, second component is the VOL. Okay, so VOL, if you see here, the VOL is not just like a zero. Okay, if you see the ideal characteristics of inverter, VOL should be 0, but here the VOL will not be 0. This is this VOL depends on the sizing of M1 transistor. Okay, this depends on the sizing of M1 transistor, and this is the complete factor on which it is going to change. So let us try to calculate somehow. Let us try to check something, how we can control this VOL. This Kn is nothing but this is the mu COX W by L. Okay, so this is the Kn. Kn is this is the mu COX W by L. Okay, so what will happen if I'm going to increase the W? Okay, so if I am going to increase the W, this Kn will increase, and if this Kn will increase, this factor is going to reduce. This factor will reduce. Okay, similarly, you can also calculate other parameters here, like what are the other parameters, and accordingly you can calculate what exactly the VOL is. So this VOL, that completely depends on the sizing of transistor M1, because this Kn is everywhere. Kn is here. So all this factor decides what is the value of VOL. Okay, if I'm talking about the simplified expression for this VOL, so this VOL simplified expression for VOL can be written as, let me write something that is given by 2 times of VDD divided by 3 Kn divided into RL. Okay, so this is the factor. This is the simplified expression. You may ask one question, like I'm expecting that you will ask the question, but you have not asked. So let me ask the question to you and let me answer that one. How to calculate these values? Okay, what are the what is the procedure to calculate VOH, VOL, and other parameters? So I will tell you what is the procedure. Okay, next parameter is the VIL. Directly the VIL, I'm just writing what is the VIL, and that VIL that depends on the VTH. VTO is nothing but this is the threshold voltage of this transistor, and 1 upon Kn into RL. So if the Kn is increasing, means the mu CUX W by L is increasing, in that case this factor will be low. This will become lower, and that VIL will be close to VTH. So the important thing is the minimum value of the VIL can be up to the VTH. This is really very important question, especially for objective type questions, right? So what is the minimum value of VIL that can be? Okay, VIL is nothing but, if you can remember, this particular point where we calculate the -1 slope, and this point is the VIL. Okay, so this VIL can be the minimum value of this VIL is equal to the threshold voltage of the transistor. But if the W by L is somewhat lower, then this factor will be increased. So the this VIL will increase. So the important thing is the VIL will start. Let me change the color. Okay, so this curve will move here in this direction if the strength of M1 is reducing. Okay, any doubt on this? Anyone? What I'm saying, if the strength of M1 is reducing means strength of M1 is reducing means you are reducing the Kn. Okay, so if you will reduce the Kn, what it means, this factor will have some value. The second factor have some value, and if it has some value, the VIL will be greater than the VTH. Okay, so initially VL was the lower, it was around VTH, but if I'm reducing the size of M1, in that case the shifting will be in this direction. So this is due to the W of M1 is reducing. So this slope point or -1 slope point will start increasing, or this VIL will increase if W of M1 is reducing. So this is really very important thing that you should consider. One more thing. Okay, so this is the factor on which this graph depends. Other important parameter is like, suppose if somehow I am increasing this value of RL. Okay, so what will happen if I am increasing this value of RL? So this point will be 0, so it will be somewhere here. So but if I am increasing the value of reducing this value of RL, so this factor will be somewhat dominating, and that will work. So this is how we can calculate the things. Okay, so this is the factor which you decide. Another thing, one more formula we have, and that is for the VIH. Okay, so what is the VIH? Then let us try to see that one, and then we will see what are the factor on which it is depending. Okay? So VIH depends on, like, VIH is nothing but this is the slope point on which we have to calculate the VIH. Okay, this is the point where we are calculating the VIH. Okay, what will happen if the size of transistor M1 will reduce? Okay, if size of transistor M1 will reduce, what it means, the resistance will increase, and if the resistance is increasing, this graph will not be here, that will shift Where it will shift? Can anyone tell me? Where it will shift?
Can you repeat the scenario again?
Scenario is like if I'm increasing this, I'm increasing the size of M1. Okay, in that case, what is the value of this VIH? Where it will shift? It will shift here or it will shift here? In which direction the VIH will shift?
Sir, if I'm increasing size of M1, then resistance of M1 will decrease.
Hmm.
Sorry, if I'm increasing size of M1, then Kn will increase.
Hmm.
So Kn will increase, then sir, I think that since minus 1 by Kn RL term is there, so it will shift to the left.
Okay. So you are saying that
If
if,
W increase.
yeah, this Kn will increase. If this Kn is going to increase, what it means, this factor will be reduced. So we can approximate this is around that will become very less. Okay.
So it
And
is minus side, right? So it will move to the right.
yeah, so it will move towards to the right direction. Okay. So the movement of this graph, yeah, let me change the color so that you will feel something. Yeah, so here the graph will move in this direction if I am changing the things like here. Yeah, so simply just let me connect it here. Something like this. Okay, so this is the characteristics if I'm increasing the size of this one. Okay, so the important thing is, I just told you before also, like if the on resistance of M1 is equal to RL, so you can achieve up to the VDD by 2 only. Okay, so the maximum value that you can achieve, that will be VDD by 2. So suppose if you have done something like this, where the point is, this point is VDD by 2, and this is the condition when RL is equal to R on of M1. Okay, so this is the condition at which you will receive the VDD by 2. Okay, so this is the characteristics of this resistive load inverter, and this is how it works. Okay, and similarly, if we can, what things we have discussed? We discussed two things. One is like what is the power? So there is no non-zero power dissipation. It will be there. So there will be definitely some static power dissipation. The noise margin, yes, noise margin is missing. So let me calculate that one. So the noise margin for low is given by VIL minus VOL. Can anyone tell noise margin, when the noise margin will increase and the when noise margin will decrease? And then
Sir, if the size of transistor is increasing, then NML will increase.
NML will increase. Yeah, definitely. So noise margin will, so we are seeing here, like if you will increase the size of transistor in this direction, like this is nothing but WM1 is increasing. Okay, so if you are increasing in this direction, then the resultant noise margin will increase. So this noise margin are the function of the sizing.
Sir, the if the WM1 increases, then the V1H is increasing. So shouldn't the arrow go up? Like,
Sorry, if the WM1 will reduce, then resistance will be reduced, resistance will be less. And if the resistance will be less, then what will happen? The voltage drop across this transistor will be less. So that will be more closer to the ground, right?
sir, no, means if the W is increasing, then Kn will
W
also.
is increasing. See, here, yeah, I have already written here. If I am increasing the WL, okay. So you're talking about IL, right? You're talking about IL. No, I'm talking about the OL. Okay, so IL will be like something like this. So you can see here the IL will be, you can see IL will shift, IL will increase if the WL is decreasing. So I have already written the relation over here, right? So this is the VIL. VIL we have calculated here. VIL will increase to this value if I am reducing further the size of the transistor. And if I am increasing, that will go in this direction. You got the thing, or still there is some doubt?
Yes, sir. Yes, sir. I got means if the WM is increasing, then noise margin will also increase.
Yes, yes, of course. So the VOH minus VIH. So this is the noise margin, and then you can relate like these two are the function of the W and L and the R L. So this is important. Okay, so let us quickly complete. I think I'm very slow in teaching. I don't know. I need to make it more. Okay. Let us talk about, suppose I have this, I'm just talking about this resistive load inverter. So there are two possibilities. There are two ways to design the layout of this one. So the important question is, like I was expecting someone will ask the question, like it is quite easy to fabricate the MOSFETs. Okay, so like whatever the MOSFET we have, either it is the PMOS or NMOS, or it is the depletion type PMOS or depletion type NMOS, we can definitely fabricate the transistors. But the question is, suppose I am considering this resistive load inverter. In that case, how we can fabricate the resistance? Okay, so there are two ways to fabricate the resistances. The first way is the diffused resistor based. Okay, so this is the first structure which we call it the diffused resistor based, and the second structure we call it the polysilicon resistance based. Okay, so if I have to, yeah, so I'm just quickly making the layout, because this layout of NMOS transistor is very easy. We have already done it. But there are two ways to design the layout of resistance. The first one will be this is the first category on which you can design the resistance, which is the diffused resistor, and the second one is the undoped polysilicon resistor. Okay, but the question is, what is the difference between these two one? Okay, so the difference between these two one is, so let us talk about first, like what is the diffused one and what are the advantages of this one. Okay, so an isolated n type or p type diffusion region with one contact on each side. So here we have two contact. So this kind of this is nothing but this is the diffusion region, and we have to create between the two terminals like VDD and the output one. So this is the diffused resistor. So this is nothing but I need to create a resistance based on the p type and n type material, and then that will act as a resistor. Okay, and similarly, the important thing is, like, the resistance is simply determined by the doping density and the dimension. So this is really very important. The resistance is determined by the, what is the doping density. Okay, doping, I will take 2 more minutes, then I will finish it up, right? So it depends on the doping density, and it also depends on the dimension. What is the dimension of this one? Okay, so dimension and the doping density, these two are the important factor. What is exactly resistance is? Dimension means nothing but this is the W by L ratio. Okay, and the important thing is, if I have the polysilicon, if I have the diffuse kind of resistance, in that case, the practical value of this resistance which we can design is from 20 to 100 ohm per square area. Okay, so whatever the per square area we have, that we can design up to 20 to 100 ohms this one. Okay, so what is the important thing is, like, if you have to increase the resistance, a long resistance is a long diffuse resistance is needed. So very large width and the length is required if you want to make a resistance in the order of kilo ohm. So this is the things which need to be considered, especially if I'm talking about the diffused based resistances. But if I'm talking about the polysilicon based resistance, so the important advantage of this polysilicon based one is like you can achieve the resistance up to 10 mega ohm per square meter, square area. So that this much of resistance you can achieve. And but the problem with this one is like resistance cannot be varied. Okay, with the polysilicon, whatever you have already the other things, so the value cannot be controlled, so the resistance cannot be controlled. Okay, so one of the advantage of this diffuse based resistance is like based on the length you can decide what is the resistance and what is the value of this resistance. But in the undoped polysilicon poly resistance, you cannot control the resistance. Like you have the fixed dimension, fixed, everything is fixed, so you cannot change the resistances. So this is the benefit and the drawback of both kind of structures or both kind of the resistance designing. Okay, so this is all about the resistive load inverter circuit.